We go on, otherwise we'll be too late to break for lunch. Who's presenting and for how long?
I believe it's Jose, and according to the schedule, it's 1 hour, 15 minutes.
50 or 15? 1 5. And that's it, right?
And that's it.
It's you?
It's Giuseppe.
Oh, it's Giuseppe, alright. I need to wait then.
Okay. Okay, let's move fast to the next presentation, which is more about the same thing that we just saw, but now practical over the testbed that we have in the first floor of the CTTC. And let me start. I mean, Jose will do most of the presentation and the demo at the end, but let me just start with some considerations on the experimental work, let's say. And this is the abstract of the talk, if you want. This is what we want to do. This is the first floor of the CTTC building. What we have here is a set of femtocells that we want to deploy in the form of a mesh. So this for us is the old wireless network of femtocells. So you will have, these are 3G femtocells though. 3G femtocells, because at the time we wrote the proposal there were no LTE femtos. Even now it's, well, I don't know of any LTE commercial femto that you might get. And another additional problem of working experimentally is that as a research center, you are not the regular customer for femtocell vendors, so it's really hard to get one of those. So, so in the end, that's what we want to do. We want to build sort of all wireless network of femtocells. This is the core network of the 3G network in this case, which is emulated. We have this equipment in the lab, and it's not S1 interface, it's IUH, because it's 3G, right? The equivalent for femtocells, right? Well, this part there we are not using in BeFEMTO because we concentrate on the, this is a node B, but we have in the lab, but we focus more on the femtocell side. And the initial consideration I wanted to make is this lower part here, which is the experimental framework that we have in the lab, which allows us to do like minimize the time for experimentation, or at least reduce it. And this is the goal of the global framework. So we designed a framework that is the one that Jose is using afterwards to present the results and to show you some figures. By the way, what you're seeing here is the grid here. This is, we assign coordinates so that it looks as a grid. And if you take a look down there, this is the packet transmitted by each of the nodes, and depending on the code of color or the data queue length or the queue drops. So these are pre-recorded experiments that Jose ran over the testbed, and at the end you will have the same thing but real running over the testbed, right? So just didn't forget to mention that. So yeah, we wanted to minimize the time. We want to focus on conceptual reasoning, ideally. Like in a simulator, you put the script there and you run the experiment, and once you have the code, of course, of the thing that you want to test, you may run many different experiments with the same setup. So that's what we wanted, but for experimentation. And we also, once we had all the patches and drivers and everything put in the machine, we wanted to forget about the low-level details. So a user of the environment just could focus on the conceptual reasoning. And this is how we attained it. We have a certain number of machines, all of them equal. So we spent one afternoon putting up all the drivers, patchers, the appropriate hardware for the experiment and everything. We generate an operating system image per functionality, for example, an access point with all the patches and everything. We get this operating system image that we configure, we put it in a server. So in this server, we have a library of operating system images that then, through some configuration scripts, we distribute to all these machines at will. So we say, machine number 1, work as an access point. Machine number 3, also work as an access point. Machine number 2, work as emulate a link. So, and we do that with all the operating system images that we configured just once in one afternoon, and then we distribute them to all these machines. So in minutes, you can completely reconfigure the user scenario, let's say. And the same thing for the wide topology. We have a certain number of cards in each of these machines that are connected to a switch, and we have some scripts that automate the configuration of this wide topology, right? And then we have this control network through where we distribute operating system images. We synchronize machines for end-to-end delay measurements. We gather the results once the experiment has finished, and we also tell each of these machines at each time instant what to do, like send these traffic flow to a certain destination with these characteristics. So we try to focus on the conceptual reasoning. And the mesh part is also in this framework. So we can completely change the operating system images that we have in all of the nodes in minutes. And then we have also the cellular part of the network. We can have access to remotely to the nodes to see how they are booting and to see what's the problem, even if they don't have an IP address. Well, this is the generic framework, and we also have some commercial equipment both for testing and for putting like routers, commercial routers in the middle of a network setup. And this is the lab that we have in the second floor of this building. If you're, this is the node B, this is the emulator, this is the rest of the 3G network. So it acts as RNC, SGSN, GGSN, and it has part of the functionality of the HLR, so enough to say that we have a running 3G network here. And these are the machines. This is the central switch with which we build the topology. The yellow cables are the control ones, and this is like regular networking equipment and network testing equipment. So going more specifically for the network of Femtocells testbed, as I said, we are building a grid. What you see here is the coordinates that Jose assigned to each of the nodes, so that we have this grid over there. And in this, we play with power. Depending on the scenario, we play with power of transmission power of the nodes, attenuators, whatever, to in the end get a certain topology and certain link pattern interconnection, let's say. So in the end, since we are testing routing in a multi-hop scenario, what we want is to have many paths between any two nodes in the network. So we play with these kinds of topologies. And this is wireless home node B, not homey node B, but home node B. It's 3G. Right? So SessionCom, and thanks to Thierry and Frederica and all that, provided us 12 femtocells like the one you see here. And what we did is globally, these two things, this is a small form factor PC where we have these marks of the routing protocol, and we connect this femtocell through an Ethernet cable to this wireless mesh router, so that all the traffic coming from this femtocell commercial, we don't have access to internals of the code of all that, so that's why we had to do this. We get all the, let's say, commercial traffic, and then we, in the end, it's IP packets for us. We put them in a geographic packet, and then we do the routing in each of the nodes. And this small form factor PC, in this case, in the setups that you will see, we just have a single Wi-Fi interface, but they are prepared to have more than one interface. In fact, in other EU projects, previous EU projects, we played with multi-radio nodes. And in the end, that's what we have. So this is the commercial femtocell, no modification to any stack, and all the traffic coming from the femtocell will go to these wireless mesh router, you could call it. And here is where the code that Jose developed is put in place. So we take the decision. This is our geo sublayer, to tell you the truth. So globally, this is our wireless home node B. Right? So in the end, what we get is this. We have this setup where, for example, a UE attached, with a regular 3GPP defined interface to a commercial femto is routed multi-hop. Sometimes packets from this UE will go this way. Sometimes packets may go this way, depending on the decisions, as you saw. In the end, they reach the local femto gateway, and in the end, they reach the core network. So all these, this device is providing the, let's say, the home node B gateway side of the story. So the core part of the story, right? And this is what I just explained, the framework that we have. And now let's move on again to the details of how the routing is implemented on top of the testbed, right?
Thanks. Okay, if you hold on till the end, maybe I will explain what's this of the project. So let's start with what we tried to. How do we implement the routing protocol we just explained into the 12-node network of femtocells that we just deployed in the first floor of this building. Okay, so we implemented the intelligence of the routing protocol in NS3, and we also want to evaluate the routing protocol not only in a network simulator, but in a testbed. What do we have to do? Do we have to implement from scratch the routing protocol in another platform for evaluating it in a testbed? Well, NS3 gives us an interesting feature, which is the emulation mode, which basically allows you to send simulated packets over real devices and receive physical packets, real packets, sorry, to the NS3. Well, this is just a reminder of how the routing protocol we just explained works. I'm not gonna enter in the details, so just recall that we have two components, minimization of the Lyapunov drift and the minimization of the penalty function weighted by this B parameter. And let's go to the implementation details. So basically, in NS3, the protocol has these building blocks. The network management in charge of sending hellos with queue backlog information and geographic information. The queue base, the data queue management, which just implements a FIFO data queue. And the intelligence of the routing protocol, which performs decisions on a per packet basis based on queue backlogs and geographic information. How does it work? Basically, we have the testbed, we have a node of the testbed, and we install NS3, the NS3 application in the node. for achieving that a packet generated in an S3 is transmitted over the testbed, we use a raw socket which just is implemented in an independent thread of the NS3 application and just is in charge of receiving and sending packets, so that when a real packet comes here, it's received by the real device and forwarded to the raw socket and then processed by the NS3 node. And also, when an NS3 node has to perform routing decisions and forward packets, the packet enters this pipe and goes over the testbed through the real device. Okay, so as we are on a Wi-Fi backhaul, how do we get the packets into the NS3 node running on the application of the wireless home node B? Basically, we have to filter the packet here by MAC destination address, so that there are some packets that are going to be processed by the real home node B, and other packets are going to be directed to the NS3 application. We do that at the real car, exploiting the MAC destination address, so that when the packet arrives to the real car, its MAC destination address is checked. If it matches a variable in the MAC Wi-Fi driver of the real device, it's processed to the NS3 node. It's sent to the NS3 node. Otherwise, it's going to the Linux stack. Basically, another issue that we have to deal with when we implement the routing protocol on the testbed was the fact that we have two queues. One located on the hardware and one located on the application. How do we deal with that? We need the total queue length of the node in order to take routing decisions. What we did is to register the hardware queue length on the RAM file subsystem, which is a file subsystem which is quick and fast to be accessed by the NS3 application. And so we can get, thanks to this file, the hardware queue length. This hardware queue length is sent to the NS3 application, and so we can get here the total queue length of the node. Another thing we have to deal with was the scheduling between the application queue, the queue located at the application layer, and the queue located at the kernel level. Because if the hardware queue gets full, the application queue must be somehow stopped. So we have to deal with some kind of scheduling between the two queues. How do we deal with that? What we did here is to use netlink sockets so that a message, whenever the hardware queue length is full, is sent from the kernel level to the NS3 application layer, indicating, okay, do not send me more packets to the hardware queue. Once the hardware queue gets empty, another message is sent for the kernel level to the NS3 application, indicating that the NS3 application can start sending packets to the kernel. So this is basically, these are the two interactions we have between the kernel space and the user space. One from reading the hardware queue length through the sys file subsystem, and one for sending this asynchronous message between the kernel space and the user space in order to schedule the two queues. Okay, with regards to the routing setup in order to evaluate the routing protocol, we have to configure two kinds of routing because of the way femtocells are connected to this equipment, which is a wireless mesh router. So at the end, in practice, what we have, in order to somehow emulate this wireless home and NoD, is to set up distributed back pressure routing for dealing with the Wi-Fi links, and setting up a static route to deal with the link of the Ethernet between the femtocell and the Wi-Fi mesh router. So that whenever a packet is directed to the UE connected to this femtocell, the Ethernet is used, and whenever the packet is not for an UE attached to this femtocell, distributed back pressure routing is used for the Wi-Fi backhaul. The network of femtocells is deployed on a very small space, and we want to evaluate multi-hop topologies because we have to evaluate the routing protocol. So we have to force somehow multi-hop topologies. How do we do that? What we did is to, since the layer 3 topology is defined by hello broadcast messages, which are usually sent at 6 megabits, what we did is to increase the hello broadcast rate at which these messages are sent, so that the range between the coverage between the range that the hello broadcast messages can achieve is minimized. In fact, we do this by patching the MAT Wi-Fi driver so that we can select whatever rate we want to evaluate. Okay, so since we have now, with sending hello broadcast messages at 54 megabits, layer 3 multi-hop topologies, now we can set up the methodology of the experiments for the evaluation in the testbed. So these are all the data set of the experiments to evaluate the routing protocol. And let's start with some reference scenarios that we tested to validate the implementation of the routing protocol. We make a very simple setup on a single hop topology, and we compare the results with those attained by NS3, so that this graph represents the throughput that we can attain at one single hop with two home and NoDs connected. And as we can see here, the throughput attained by the testbed is quite similar to those to the one attained by the NS3 simulator. So we can say at this point that the emulation mode is able to forward packets without incurring into performance degradation. these are some statistical experiments that, well, these are some results that show the statistical variance that we can get at different software loads. We can see the high variability that we can obtain in the testbed. And these are some results that we get when we configure 2 hops. When we configure 2 hops, we start to get some significant difference between the testbed, which has quite a significant variance, and the simulator, which is quite more ideal than the real thing. But this variability is caused by the multipath environment in which we are, since we are evaluating the routing protocol in an indoor office, we have significant multipath problems, and so propagation errors, which are the cause of this variability obtained with different replications of the same experiment. Here we can see the from a given offered load the variance of the output attained at 2 hops of the destination with several trials of the same experiment. We can see how the variance that we can get is quite high, no? Right? Okay, so now that we have validated the implementation, at least for very reference scenarios, we wanted to evaluate the state of the Wi-Fi links, also using NS3 emulation. And we carried out different experiments during working hours and during night, using hello broadcast messages as proving packets for evaluating the Wi-Fi link packet delivery ratio, so that we can calibrate the testbed and we can have an idea when we evaluate the routing protocol in generic setups. We can see here that for every link, the variability experienced during the day and during the night is quite different. Precisely during the night, we experience quite low variability in the same link that during the day. During the day, given that we have mobile obstacles, variability of Wi-Fi links is quite more high. So going to the evaluation of the routing protocol with several flows, we performed an experiment in which 6 flows, 2, 4, and 6 flows were injected to this node here for different. We injected 2, 4, and 6 flows, and each flow injected 1 megabit. The parameter B was set up to 100. We still haven't evaluated the variable B algorithm in the testbed. It's future work to do. And we performed this experiment 15 times for every number of for every offered load injected to the network. Moreover, we wanted to evaluate the impact of the Wi-Fi link rate configuration on this experiment, and we use sample rate algorithm in order to have an idea of which Wi-Fi link rate should be the more appropriate. In this graph, we saw the choices taken by the sample rate auto rate algorithm for the Wi-Fi links, and we plot the distribution of the packet delivery ratio of data packets given the choices of the sample rate algorithm. And we can see how it seems that the 36 megabits was the more used choice by the sample rate algorithm, and this one of the choices that we take afterwards in order to evaluate the routing algorithm using fixed Wi-Fi link rate configuration. We choose this, and we choose also this in order to get to have an idea if this algorithm was able to get an appropriate estimation of which was the appropriate link rate configuration. And results show that on the one hand, results show that on the case of 2 and 4 flows injected into the network of femtos, the rate, the achieved good was not different for the different rate configurations. But on the case of 6 flows, we get an upper bound on this testbed setup. And as we can see here, the one that better behaves was the one offered by the 36 megabits configuration. Sample rate shows more variability, given that the behavior of this algorithm is to try to go on a higher rate if no losses are experienced. And the 54 megabits was the one that got the worst results. Other key aspects that we wanted to evaluate was the degree of load balancing of the routing protocol. We performed different experiments with different B parameters. In fact, we go to the extreme cases. We have here the extreme case in which there are no routing decisions taken by the penalty function. B is equal to 0. Decisions are just taken by using queue backlog information. We injected a flow from this node to this node. This node has just 2 networks, and over time we plotted the number of packets forwarded by every network, forwarded to every of the intended network here. We got that no matter the distance to the destination, both networks share approximately the same number of packets. We repeat the same experiments, but increasing the B parameter. And what we found here is that the closer network got all the packets, and the farther network do not get any packet. Well, this serves to validate that the load balancing part of the routing protocol was also working. And now, if nothing has happened in the first floor, we will try to do a live demo of what we are already showing here. These are just offline experiments that we carried out several weeks ago, and now we are gonna try to do a live demo. So the first experiment that we want to show, I will explain here, is, okay, let's try to send a flow of 2 megabits from this node to this node using a high degree of direction in reaching the destination. So let's give a high emphasis to the penalty function. Let's close this and let's execute. Okay, let's pray now. Okay, as we should see, like, that the routing protocol is okay, it's working. That's good, that's a relief. It's sending packets. This node, we are painting the number of data packets transmitted by every circle here, which represents a home node B. And they are getting to this node. Here, what is happening in this node is that it's seeing 2 networks available, because just in terms of coordinate assignment, it's behaving as a grid. And so Wi-Fi links may not follow a grid, depending on the variable environmental conditions. And as we can see here, as these 2 nodes are closer to the destination than this node, here we can see how the traffic is being distributed. Here, traffic is not being distributed because here there is a brick wall. And usually this Wi-Fi link is not working. Configuration is a single radio, single channel for all the nodes here. Okay, the experiment has just finished. And now let's try to repeat the same experiment, but decreasing the B parameter so that all the network can be used. We do this by decrementing the B parameter to 0. So in principle, we should see here that all the nodes, if Wi-Fi links are in a good state, are being used. Okay, let's pray another time. Okay, the experiment just started. And here we have how those nodes that have now stable Wi-Fi links are being used. It seems that this node now is not working very well. This node is working. The traffic is directed to this node, which is not transmitting packets. It's a unidirectional flow. Now this link is working. Note that the number of transmitted packets at every time slot by every node may be different due to the contention issues of the CSMA CA medium, because now we are on the real. Now we are dealing with the real thing. And now let's try to execute a multi-flow experiment. Now we are trying to send to this node 6 flows with a high degree of direction. B is configured to 200, which means, given the hardware queue length of the nodes, that means basically practically null load balancing in the network. And these are the nodes that are chosen for sending traffic to this node. Okay, experiment started. We should see that just these nodes, okay, just these nodes are being used. null load balancing. This means that these nodes in principle shouldn't be used, this set of nodes here. Also note that there is a tendency to have the color of the nodes tend to be darker near the destination than farther of the destination. Yeah.
Wouldn't it be better to use a fixed density scale in order to have a better mapping on the darkness of each color? Because I see that on the right hand of the screen the scale changes, the number of packets, I suppose. It would be better to be fixed in order to know the correspondence of the number of packets and know whether the dark corresponds to 500 packets, let's say, each time, and not to change on a per second basis, perhaps. It would be better, visually talking.
A percentage of packets or something like that.
Yes, or a fixed number, perhaps, because from second to second this changes, and you do not know whether the black color is blacker than the previous.
Yeah, the thing is that I got your point. Yeah. But if you change, a percentage will be. But the problem, I think, is that if you change the offered load, the scale should change also. So it's like. Yeah. Yeah. You're right. Yeah. Thanks. Okay, so let's go back to the conclusions of this talk. Okay, we have given some hints on the implementation of the routing protocol, also given some results of on the evaluation of the routing protocols, and one of the main conclusions is that if you want to get simulation and experimental results, I would go with NS3, because you don't have to re-implement twice the thing. At least if you want to test functionality. For proof of concepts, I would go with NS3. You will invest less time implementing. Okay. So that's all. With this, I conclude.
Okay, thank you. So what's next? What is coming now?
Well, now I'm obsessed with this B parameter.
All right.
And pretty obsessed.
Now the thing is that, as you know, the last phase of the BeFEMTO project is about exhaustive evaluation. So first year was about concepts, second year about mechanisms, and this up to June we are like testing exhaustively what we designed, and for sure we will have more ideas, like maybe testing different cost functions, and preparing the demo for the final audit also. Yeah, this is part of it, in fact.
This was an initial demo, no? Show some initial things.
Yeah, that's it.
Well, yeah, it's like with cooking, you know, you spend a lot of time preparing the food and you eat it in 5 minutes. So it's a bit like here, you spend a lot of time, years and years, and then it's, 10 minutes showing a colored graph. So it's difficult, yes, but it's definitely worth it.
Yeah, sometimes in experimental research, the testbed setup section is a small percentage of the paper, but in the end, it's the 70 or 80% of the time of the paper, let's say. Yeah.
20/80 relationship. Okay. There are more questions? Yeah.
I was wondering, was it really difficult, the interaction between NS3 simulator and, to use the functionality of emulation for emulation? Because I think this is a very interesting,
Yeah, it
and many
depends.
people want to know, and also ask me, by the way, because I'm working with NSFree,
Yeah.
and many people telling me, I know that functionality of emulation. Was it hard? Did it cost a lot for you? I mean, the coordination between the two schedulers, the kernel
Yeah.
queue and the application queue in NSFree is.
It basically depends on the particularities of the network protocol, if it's a network protocol that you want to test. In this case, as I have to use queue backlog information, I have to do this scheduler, because all the functionalities that I need to do the routing decisions were implemented at the routing layer, not at the MAC layer.
Yeah, yeah,
And,
yeah.
but
It depends
if
on
you
the
want to implement to port to the testbed OLSR, for instance, you don't have this problem.
Yeah.
This problem was caused by the particularities of the back pressure. You need this information to get routing decisions, but for instance, OLSR doesn't have this problem, so you don't have to this extra work. And the intelligence of the routing protocol, I didn't have to change a single line of code. That's important.
Yeah.
Changes were just on the data plane, not on the control plane. Well, on the next hop building block, you know, on the building block that has to compute the routing decisions. I didn't have to change a single line of code.
Okay, thank you.
All right, excellent. Any other question? If not, thank you very much, Jose. That's it. No further presentations.
No.
All right, so I think we're coming to the very end, Friday afternoon, and I think we had a pretty productive, inspiring week. Maybe beat only because we have been taken away from our emails and usual working routine. Just have a bit of time getting inspired whilst listening to presentations, thoughts, new ways of presenting, doing things. We have been going through the business case, and that was pretty important just to show, you know, it's not only R&D driven, but it's also market driven. What we're doing here has a real impact in the end on engineering solutions, on customers, on businesses, large or small. We moved on then to some physical layer challenges, loads of challenges there highlighted, propagation issues, planning issues, radio resource management interference issues. Then we went on to the optimizing that all, self-organizing stuff. Today we had networking issues. So I think we have a pretty good picture. It is clearly very far from complete, but I think it gives you who have come as attendees enough building blocks now to know where to look up information, to know whom to email, to ask, to call, and you know, just get essentially the R&D going in the area of Femtocells. So without further ado, thank you very much for attending. Thank you very much for talking. Goodbye.